Hello guys, nice to see you. Okay, do you hear me this time? Okay, cool, thanks. Good, then I would like to start with a short recall of our previous topic. So we have shown last online lecture that there is a relationship between scalar field, which describes electrostatic potential distribution around an electric charge, and vector field, which is described electric field around this electric charge. So in other words, by doing certain mathematical operations, we can go from scalar field distribution of electrostatic potential to vector field distribution of electric field. And there is a relationship between these two electrostatic potential and vector of electric field. So we change the screen. We have shown that for the taking into account the spherical symmetry of the electric field of a point charge, we can write electric field vector at certain position vector r will be minus dv over dr. So it's derivative over distance. In other words, how fast electrostatic potential changes along the direction of a radius vector, which originates from the point in space where the source of electric field, the point electric charge, is located. In general, we have some three-dimensional case, so we can consider projections of this electric field vector on different axes, and that is taking into account, we are applying such so-called gradient operator, and that's why for three-dimensional case, you can write that it's always possible to calculate electric field vector by applying this gradient operator to scalar field, like field of electrostatic potential. Will be minus this gradient operator times v, and this will be minus dv over dx. Here we have unit vector I along axis x plus dv over dy, unit vector j plus dv over dz, unit vector k. So this is the general relationship between electric field. vector and distribution of electrostatic potential around this source charge. So this is refreshing the information which we discussed on previous lecture. It's kind of important relationship. Please try to keep it in mind, because very often it's much easier to calculate according to superposition principle electrostatic potential, since it's just an algebraic sum of scalar quantities around electric charge. And then from knowing this scalar field, which represents electrostatic potential distribution, calculate by applying this gradient operator the electric field vector in any point of space. Then, in the contrary, calculate the sum of vectors, electric field vectors, in each point. That could be much more complicated task. Okay, so today we continue with trying to proceed further with the analysis of electrostatic potential. In particular, we will discuss electrostatic potential next to some distributed charges, like some continuum of electric charges. And we considered last time just distributed point charges. Today we will talk about distributed continuum charges, and we will try to consider also some practical case how we can determine electrostatic potential next to some distributed continuum of electric charge. And we will show that it could be much easier to determine electric field vector from this electrostatic potential distribution than to do it in the contrary, what I mentioned before, that sometimes it's really much more difficult to calculate electric field vector initially. Okay, so let us consider a body with some continuously distributed electric charge, and we are interested in finding electrostatic potential value in point P next to this continuum of electric charges. So we can divide this, as usually we do, in small parts. For instance, we can depict here two small volumes, and let's call it small charge Q1, dQ1, and here dQ2. So there is some distance from these small volumes, which we can consider as point charges to this point P. So let's consider R1, R2. Since we selected very small volume with the electric charge dQ1 and dQ2 and dQ so on n, in order to cover all this body, the distance from the point P to this small volumes we consider is much larger than linear size of these volumes. And that's why we can consider apply regular equations for a point electric charge while we deal with each of them separately. So in this case, some small electrostatic potential dV, which results from electric charge dq, can be represented as Coulomb constant times dq divided by r, which is the distance to the point where we want to calculate this electrostatic potential. And obviously, we need to integrate all over these small electric charges to take into account contributions from each part of the continuum. So in this case, in order to calculate the total resultant electrostatic potential at point P, assuming also the superposition principle, which is valid for this, for calculating electrostatic potential, we can write that electrostatic potential is equal to Coulomb constant integral over all small charges. We divided our continuum divided by r. So this is the way how we deal when it's necessary to calculate electrostatic potentials of some originated from a continuum of electric field and of electric charge. And now let us proceed further and consider some real example, so you have better feeling how it works. In this example, we'll consider the same system which we actually considered earlier, and that is kind of good because we can compare how easy or difficult will be to get the answer when we proceed with the same system, first calculating electric field vector, and then with another approach, we first calculate electrostatic potential and calculate electric field vector from the relationship between electric field vector and electrostatic potential. So now let us consider a disk. So we have some system of coordinates x, y, x, y. The radius of the disk is r, capital R. Then we need to, so it also uniformly charged with some surface density, constant surface density sigma. And let's consider that it's positive charge. Then we need to define some surface element, like some small surface element, which we first consider as a point charge, which will create certain electrostatic potential at point P, which is at the distance along axis x, so its coordinate is x. So let us assume some small surface element of this disk, and it will be something like this. This is position vector r, and here is angle theta. and this part is dr. So that's why we can define this small surface element. We did it before. It is position vector r times d theta in radians and times dr. So this is the area. So this defines length of one segment of this area, and this defines the other one. So the product gives us the area. And as a result, we will have some small electric charge defined by this small area, which will be sigma. We have uniform surface density of electric charge times r times d theta times dr. So in this case, we want to calculate what will be the electrostatic potential created by this small surface element at point P. And following to this equation, which we know for point electric charge, this small electrostatic potential originated from this small charge dq will be Coulomb constant times dq divided by distance from the electric charge to the point where we calculate potential. And this distance will be square root of r square, this position vector of the, which defines position of this small surface element, plus x squared. Distance from the center of the disk to the point P, which is located on the axis x. So now we can substitute, instead of dq, its expression. So it will be ke sigma r d theta dr divided by r squared plus x squared. Okay, in order to get the total electrostatic potential, following the principle which we considered on the previous slide, we can write. So the total electrostatic potential at point P will be, so Ke and sigma, they are factored out from integrals because these are constants. And we have integral from 0 to 2 pi d theta times integral from 0 to r, like capital R, which is the radius of the disk, r dr square root of r square plus x square. And here, this first integral is quite simple. It will be just 2 pi. So we have 2 pi Ke sigma. Here we need to put this r under the differential and add x squared as a constant, because in this integral x is a constant. Then we will have 1 second here in front of the integral. It will be dr squared plus x squared. And here is square root of r squared plus x squared. So, okay, this will be equal to k. So we have actually these two cancel each out. So we will have k e sigma y times square root of r square plus x square divided by 1/2. That's our integral, and this we need to take to consider in the range from 0 to r capital. So we will get, now these 2 will go here in the denominator. It will be 2 k e times pi times sigma. And if we consider capital R instead of R, it will be capital R squared plus x squared minus, if we consider 0 instead of R, it will be just minus x. Okay, so this is our expression for the electrostatic potential at point P, which is located at distance x along axis x from the center of the disk. Now let's keep this in mind and let's write this equation again on this next slide. So it will be a 2 k e pi sigma times, okay. So electrostatic potential will be equal to 2 k e pi sigma times square root of r squared plus x squared minus x. So now we want to determine the strength of electric field at the point P. And in order to do that, so it will be x component of the electric field. And we know from considering this case previously that will be only one direction where electric field will exist. So it will be alignment of electric field vector along axis x because of the symmetry of the disk. So all these components in direction y, they will be canceled by symmetric electric charges selected on the disk. And for each segment of area which you select on the disk, you will always find a symmetric surface area because of the symmetry of the disk. So in this case, electric field, it will be aligned along axis x. And in order to determine this electric field, we need to know how fast electrostatic potential changes along axis x. So that is taking the derivative, it will be minus dv over dx. So from definition of relationship between electrostatic potential and electric field vector, which we described on the previous lecture. And now we need to take derivative of this. So it will be, so we have this minus here, and 2k e pi sigma. Here it will be 1 second. Here will be square root of r square plus x square. And since it's a complex function, we take derivative second time of this x square. So we have 2 times 2x. And here will be just minus unity, because derivative of x is unity. And we can cancel out this. Why it doesn't work anymore? It is strange. Okay. Sorry about this. Then finally we can write 2 times pi times k e times sigma 1 minus 2. Oh, sorry, there is no 2 anymore. We cancel it out. Will be minus x divided by square root of r squared plus x squared. And as you may remember, this equation we derived previously when we calculated electric field vector of this at point P created by uniformly distributed electric charge over a disk. So that was way more difficult to do the calculation, even taking into account the symmetry features, than to take derivative of the electrostatic potential, what we did here. And eventually, regardless of 2 different approaches which we applied here, we get the same result for the electric field vector at point P. Okay, so now it is clear how we deal with some real cases and operate with the determined electrostatic potential continuum of electric charges, and then we can take derivative in certain direction, or in find the gradient when we have 3-dimensional case and we need to take partial derivatives along each 3 directions, x, y, and z, and that is the way how we calculate electric field vector. Okay, now we need to proceed further with the electric potential due to a charged conductor. So we already had a discussion previously on features, like conditions which have to be satisfied for conductor under electrostatic equilibrium. And we remember that one of the conditions was, like, actually a few of them. Let's say if we have some conductor under electrostatic equilibrium, and that conductor carries certain electric charge. Let's say it has some positive electric charge. This electric charge is allocated on the surface of the conductor. There is no electric charge inside, and also the electric field lines are always perpendicular to the surface of such a conductor, which carries electric charge on its surface and remains under electrostatic equilibrium condition. So these are electric field lines. So now let us consider 2 points on the surface of this conductor. Let's say we have point A and point B. So there is some path which connects these 2 points, and this path goes along the surface. So it goes always along the surface of the conductor. So in this case, it doesn't matter which point we select on this path. At every point, there will be one condition which is valid because of the electrostatic equilibrium of this conductor. So if there is some path which connects 2 points on the surface of this conductor, it will be always, the electric field vector will be always perpendicular to the displacement vector along this path, which lays on the surface. And assuming this, the dot scalar product of electric field vector and the displacement vector will be equal to 0, because we have this scalar product. It will be magnitude of 2 vectors times cosine alpha, and this alpha is angle between 2 vectors. If alpha is equal to 90 degrees, then this cosine 90 degrees will be equal to 0. So there is 0 product. And in this case, if we want to determine the potential difference between these 2 points, we will end up with this: potential at point B minus potential at point A is equal to minus integral from A to B along this path which goes through the surface, like along the surface, scalar product of vector E times ds, and this is equal to 0. So it means that there is no potential difference at any 2 points on the surface of a conductor which carries certain electric charge on its surface and remains in the electrostatic equilibrium. This result is valid for any 2 2 points, as I mentioned before. And that's why the surface of a conductor with under electrostatic equilibrium can be considered as equipotential surface. So it fits to the definition of this equipotential surface. Another thing which is important to mention, that since we know from the conditions of electrostatic equilibrium of conductors, inside electric field, inside of this conductor, electric field is equal to 0. And electrostatic potential, as a result, since we know that electric field vector is defined as gradient of electrostatic potential, it means that electrostatic potential inside the conductor is constant, so it doesn't change, depends on position where you consider it, and it is equal to the electrostatic potential of the surface of this conductor. So in order to show it more clearly, let's go to another slide, and let us consider a sphere with some uniformly distributed positive electric charges on its surface. So it means that this sphere is a conductor with which carries some electric charge, positive electric charge distributed along its surface, and it is under electrostatic equilibrium. So this is the center of the sphere, and we can draw the following. So here we can show the potential. So it will be R position. Here is V potential. And inside this surface, inside this sphere, up to its surface, this potential will be constant. So it doesn't change, and it will be equal to the potential of the surface. And in this case, it will be K E times Q divided by capital R, which is the radius of the sphere. So if we go further from the surface, electrostatic potential, of course, will be reducing, and that will follow the dependence K E times Q divided by R, which is distance from the surface to the point where we determine this electrostatic potential. So since inside of this sphere we have constant electrostatic potential, and we know, let's say, that E R in the direction of position vector will be minus dV over d R. If there is no change of electrostatic potential in the direction of certain radial direction, it means that so in this case, it will be equal to 0 because V is constant. So that fits into the condition for electrostatic equilibrium of conductor. We know that inside of electrical conductor, electric field is equal to 0. So here we have electric field. And here we have also R. So inside, from the center, like everywhere inside the sphere, up to the surface, our electric field is equal to 0. And once we reach the surface, it jumps to certain value of electric field and then decreases, which will be, this decrease will follow the equation of like Coulomb law, which takes into account symmetry of the sphere. That will be Ke times Q divided by R squared. So this is what we need to know about electric field and electric potential distribution inside the conductor, which carries some electric charge, and on its surface, and also at certain distance from the surface of this conductor. Now we need to figure out one more thing, that in this example, we consider a sphere, so it's very well-defined symmetric body. And that's why sigma, surface density of electric charge, which is distributed on its surface, will be constant. It will not depend on any position of the surface, so means for any point on this surface, sigma will be the same. However, it's not true when we have some random shape conductor. And in order to show this, let us consider two spheres which are connected with a conducting wire. So that means that they're, let's first define. So it is radius 1. Here we have radius radius 2, and we have Q1, Q2, we have V1 potential and V2. And of course, there will be E1 electric field next to its surface, and E2. So, since these two spheres are connected with a conducting wire, that means that their potentials are equal. We can consider just some potential V. And since their potential is equal, the potential of their surfaces, we can write that Ke times Q1 divided by R1, so it equation which defines electrostatic potential of sphere 1, is equal to Ke Q2 divided by R2. From here, we can cancel this out, and we can write that the ratio Q1 to Q2 will be equal to the ratio of their radius, R1 to R2. So now let us write expressions for the electric field. E1 will be equal to Ke Q1 divided by R1 square, and E2 will be equal to Ke Q2 R2 square. keep in mind that electric field will not be the same, only electrostatic potential. So now let us find the ratio between E1 and E2. So from here we can see that we have Q1 over Q2 times R2 squared divided by R1 squared. Now we know that this can be represented in terms of the ratio of radius. So now we will substitute this instead of this. So let us do it on the next slide. So E1 over E2 is equal to R1 divided by R2. So instead of Q1 and Q2 times R2 squared divided by R1 squared. So now we can cancel these squares, and it will be R2 divided by R1. So what it tells us? It means that electric field, for instance, let us consider that R2 approaches 0. So the curvature which defines the radius which defines the curvature becomes very small, means that this curvature becomes kind of very sharp. Then from this ratio, it means that E2 should approach to infinity in this case, because we need to divide E1 by some very large number to get something close to 0, which we have here because we have R2 close to 0 in the denominator. So it means the smaller radius which defines the curvature, the sharper the surface structure, the larger electric field at the same surface potential, because you remember that for both cases, regardless the radius of these spheres, we have the same electrostatic potentials. And that is actually known. So because of very significant increase of electric field next to sharp elements of the surface of conductors, this strong electric field could cause acceleration of electrons, which are always present in air. And because of impact ionization, these accelerated electrons will ionize like air molecules, oxygen and nitrogen, and they will recombine, resulting in some glowing mostly in UV region. So this effect is called corona discharge, and that could be observed next to some sharp elements of the high voltage surfaces of some power grid or some facility which deals with very high electric potentials. And that, of course, electrical losses, so people are trying to eliminate as much as possible these corona discharges. But that is what's happening when we have locally very sharp conductor surface charged, where electric field, regardless, it could be quite low potential, but if the surface curvature is very large, then electric field could go to very high values. So also I would like to discuss before like next 2 minutes some practical applications of electrostatics. We were considering these theoretical concepts and aspects of this. However, it would be also useful to consider some spheres and like fields where these electrostatic concepts are applied in practice. Okay, do you guys see my slide?
Yes.
Okay, cool. So one of the application is so-called Wonder Graph generator, so which consists of we provide certain not very high potential to this transport line, which transport electric charges to this sphere mounted on insulators, and with certain needles, it collects charge from the transporter and accumulates in this sphere. So this can continue quite for a long time until electric field strength next to this surface is not reaching up to 3 millions of volts per meter, when we have electric discharge, so-called breakthrough or breakdown electric field for air, like dry air, then we will have losses of electric charge because of these discharges where air, which is not conductive, but at very high electric fields, it becomes conductive. So up to about 3 millions volts per meter electric field next to this sphere, this electric charge can be accumulated, and then it can be used as accelerator of electric of some ions for certain experiments, like some bombardment of different materials with different ions, and see how their properties are changing. So this is one of the simple and straightforward way to create such accelerator with quite high accelerating voltage. Another application you maybe quite familiar with is actually application in our laser printers, which we use quite often everywhere. So the principle that this cylinder, where we show the expose the image or text which is supposed to be printed, it is first initially electrically charged, then treated by laser or some light exposure in order to remain electric charge only on those areas where the image or text should be. Then it's covered by negatively charged toner, like some powder, printing powder. So it sticks only to that areas of the surface of this cylinder, which remains electrically charged. And then when we print, there's high temperature, this toner is sintered, like baked, and transferred on paper. And of course, it's transferred only from those parts of the cylinder where toner was electrostatically attached. And that's why we get like very sharp and clear text and images by means of this laser printing technology. Another application which is quite common, but mostly in some industrial applications, this is electrostatic filter. So there is some initial filter for big particles in exhaust, like industrial exhaust systems. Then it goes through some metal grid which charges these particles, let's say positively, and then electric grid with negative potential, which absorbs these positively charged particles and keeps them from going outside from this exhaust in the industrial plant. So which can help quite a lot with saving environment around these industrial areas. Then when this collecting grid is kind of full with these particles, it is replaced and cleaned. And then of course these waste particles can be properly utilized instead of being spread all over the square kilometers around industrial plants, which is really very bad for the environment. Okay, so this is like just some general applications of electrostatics in industry and our everyday life. And there are, of course, more of those, but I think that few examples are quite convincing that besides fundamental value of the physical concepts which come from the electrostatics, and are used further in different fields. It also matters for real practical applications and makes our life better and more convenient and safer. Okay, guys, so I think we are already quite significantly out of time. Thank you very much for attention, and wish you good evening. So we will meet on Friday, and there we will start a new topic, which will be electrical capacitors. We will learn everything about electrical capacitance, and that is another thing. It's interesting from the point of view of fundamental science and like some application of knowledge we gain while studying electrostatics, but also in practical application, capacitors are used in all electric circuits in many quantities, and that's why it is very important concept to understand, because you can find electrical capacitors pretty much everywhere, starting from your smartphone, computer, or some high voltage power grids. Okay, thank you very much for attention, and have a good evening and take care. Bye-bye.
Goodbye.
Mm-hmm.